Hello everyone, welcome to lecture number 5, Computer Science 401. Okay, today's stuff, which is today we'll be talking about again something not that useful, but in my opinion can be interesting. Okay, we'll be talking about compilation process. Okay, phases of compilation. Okay, so in a typical compiler, compilation process proceeds through a series of well-defined phases. Okay, which is shown, which we're going to kind of like not draw, but write. Okay, so what are those phases? First off, at the very beginning, which think about what a computer is reading. Okay, so you just wrote a file, that Java file, right? And you supply that to the compiler. Okay, so first off, let's talk about the higher level. Okay, procedure. Okay, so at the very top, you have a source program, a source code, right? Um, if we're talking about C++, okay, then it goes through preprocessor. Okay, so in C++, you have um, preprocessor directives. I don't think you have it really. I think you do have it in Java, but it's not that useful. Okay, but in C and C++, it's used all the time. Okay, yeah, so define. Okay, so here's an example. Here's a good example. Okay, so this is the array, right? That's also array. Okay, in C. And the stuff which starts with the hash mark, okay, that's called the preprocessor directive. Okay, so for example, in this case, it says define table size equal to 100. So what it means is that the very first thing that compiler is going to do is going to go through the code and it's going to simply substitute text-wise. Again, we're not talking about like programming or anything intellectual. We're talking about simply substituting all the text which matches this regular expression table size with 100. So just simply like finding and replacing. Okay. So in this case, after the preprocessor directive is going to be executed, again at the very first stage of compilation, those table size will be replaced with 100. Okay. Or for example, something like this. If I say get max AB, it's going to be simply replaced. Again, we're talking about textual replacement of this, okay, with this. Okay. Define table size 100. Okay, so it's going to replace table size with 100, and then you have undefined. Okay, so basically cancel that. So cancel the table size is equal to 100, and then define again the table size is equal to 200. So again, syntactically, everything which starts with that pound sign is called a preprocessor directive in C++. Okay, I think I've seen them in Java. It's just like they're super rarely used. In C though, it's just extremely important. Okay. Cool. Okay, we have source program. Okay, so again, the code that you wrote, it goes through preprocessor, then it becomes modified, right? So right after we just substitute all the text, okay, it becomes modified source program. Okay, then it goes to through C++ compiler. Okay. Okay, then it becomes C code. So I'm not sure if you know, but C++ is built on top of the C. Okay, and the compiler from C++, all it's doing is converting the C++ code into the C code. Okay, so it's not really compiling immediately into zeros and ones. It just gets it into the C code first. Okay, and then it compiles C code using C compiler. Okay, and then you get assembly language code. Okay, so that's overall like hierarchy. That's basically how, just in general, how it works. The compilation process works in C++, but that's only high overview. So now let's get a bit more detailed. Okay, so what happens specifically with the compilers? Okay, what does a compiler do? Or like this one. Okay, in general, like languages like C, Java, C++, C Sharp. So again, at the very beginning, right? So when we have modified source program, okay, that technically to a computer, it's nothing apart from the character stream. It's just a bunch of huge set of characters, right? So any kind of code for a computer, again, at the very just like at the bottom of it, in a nutshell, it's just a character stream. Okay, so we have a character stream at the beginning, which we read, right? And it goes through special tool, which is called scanner. Okay, or in other words, it's also called lexical analyzer. Okay. Now, if I was teaching that in person, I would be like asking you, like I'll be asking you a lot of questions and like what it looks like. Okay, so but so character stream again, just like all your source code, just stream of characters, right? You scan it, and then what do you do? The scanner and lexical analyzer, according to some regular expressions, it's trying to break all the characters into modules. Okay, so again, for example, if you have some code like int I is equal to 0, right? So what the scanner is doing, it matches all the code you have against the regular expressions, and it's breaking them down into tokens. So it's the very first thing it needs to do. It needs to understand that this I is not I by itself. It's int. Okay, and int is going to mean something which we're going to figure out later in the future, right? So int is the first token, then space, okay, is going to be removed. Then I, okay, so just basically any kind of character. And then this one is equal sign, right? So it's not I equal sign, right? No. I is separate from equal sign, and of course spacing has nothing to do with it. Okay, so this is not a separate I character. No, it's int. Okay, then we have I. Okay, then we have equal sign. Then we have 0, which is a number, and then we have semicolon. Okay, so lexical analyzer, its task is to break down the whole character stream into tokens, so-called token stream. Token stream. Okay. After that, that token stream is being supplied to the parser. So parser, well, yeah, okay, which is syntax analysis. Okay, and that is even that's already more interesting. So parser, syntactic analyzer, and the parser, what they're trying to do, they're trying to make sure that it technically makes sense to place I in T first. Okay, then you have I. Yeah, well, first off, if a scanner, what can go wrong in this stage? Okay, so for example, if you put some kind of a Chinese character here, like if I put a Russian character here, I don't know, like, well, like this, okay, then of course that's not going to work, and the scanner is going to raise a question. It's going to show a syntax error. Okay, scanner is going to complain about the fact that this character does not match any particular regular expression. By the way, that if you take a look at the lexical analyzer for real programming languages, it will be built on like thousands of regular expressions. Thousands, literally. I remember I was taking a class at UC, was compiler design. We were creating compilers from scratch, and we would just literally, so imagine writing regular expressions for everything, for all possible code in Java. It's insane. It's insanely difficult. Sorry. Okay. So again, if a certain character doesn't match a regular expression, then scanner, lexical analyzer, is going to raise a question. It's going to say, hey, what the hell? Like, I don't see. So, no, like later, we're going to try to. It's going to try to analyze the meaning of each token, okay, and if it's possible to place them together. But here, like if I see something which I'm not familiar with at all, then it doesn't really make sense to go any deeper. That this code is definitely wrong. Okay, that's what it's saying. Okay, so if any part of the code doesn't match a regular expression, that means we're done. That's it. We're raising an error. We're raising a flag, red flag. Okay, and we're throwing an error. We're saying we're not going to proceed any further. Okay, now in terms of the parsing, okay, what mistakes is trying to avoid here? Also, it will be syntax mistakes. Um, for example, mm, how to say that? So at this point, it's mostly thinking about grammatical rules. Okay, so it's trying to understand if it's possible in that, according to Java grammar rules. Remember how grammar works from Computer Science 350. According to the Java grammar rules, is it legal to say int first? Int first. Is it legal? Then is it legal to say I second? Then is it legal to say equal sign? Then is it legal to say 15? Is it legal to say um, um, semicolon at the end? How legal is it? Okay, according to the grammar rules. So the grammar says, similar to how grammar works in English, right? Grammar says that int needs to go first, right? You can't do int, that's not allowed. You can't do equal sign, okay? So the order is very important, and that's what the grammar is forcing, and that's what the parser syntax analysis is trying to make sure you did it correctly, okay? So the scan and lexical analyzer doesn't really care about that. It's just breaking the whole stream into a sequence of tokens, and technically this is a token that's legal, this is a token that's legal, this is a token it's legal, 15 is a number that's also legal, semicolon also a legal character. Okay. After lexical analyzer, make sure that all the characters can be read properly, breaks them into tokens. The parser is making sure that the grammatical rules are enforced. Okay. So after that, we build a parse tree, right? Yeah. So we build a parse tree. Okay. We're gonna learn it later, I think, in this course, how to build a parse tree, and then we're getting into semantic analysis. Semantic analysis. Okay, and intermediate code generation. Okay, cool. Okay, after that we're getting, so that tool, semantic analyzer, is giving us abstract syntax tree. Okay, yeah, we'll be talking about that later, and then that is supplied to machine independent code improvement. Okay, so machine dependent code improvement, what would that be? Let's say you have code which is legit, okay, but it has some minor or huge things which are not necessary. For example, um, let's say you have int I is equal to 0, int a which is equal to I plus 2, okay, and then later on you never use an I. Later on you never use an I is never used. Okay, then not really, regardless of what kind of machine you're using and what kind of computer you will be using, it doesn't really matter, because I is used only once. It's here, right? So what is the like smart compiler is going to turn on optimization, is going to think, okay, so what's the point of using I anymore, any further from here, right? Let's just replace this I with 0. That's it, and let's just delete this code. Okay, and then let's just say like int a is equal to 2. Let's just do this. Okay, so again, doesn't really depend on, doesn't really matter what kind of processor you have, doesn't really matter what kind of programming language you have, right? So that improvement is really machine independent. Okay, and there are a lot of stuff like that. There's actually the whole section in computer science theory which is dedicated towards how to catch things like that, very small improvements or huge improvements, um, basically how to predict how the code can be optimized, and a lot of times, I don't know, like half of the code can be removed and optimized through, depending on how aggressive that optimization is in. Cool, hope it makes sense. Machine dependent code improvement. Okay, now after that we have modified intermediate code. Okay, modified intermediate code. Then we come into a part of the compiler which is specific to your processor. Okay, so keep in mind that what compiler is doing. Okay, it's converting int I is equal to 0, right, into stuff like 0, into like 32-bit instructions, okay, which look like 1 1 1 1. Okay, so it's, let's do 0 0 0. Okay, so it's 8 bits, right, 16, okay, and 32. Okay, that's what it's doing. And every single processor by every single manufacturer, for example, we have Intel, we have Qualcomm, we have IBM, we have Apple. Technically, they're all different processors. TI, okay, they also produce their processors. They all may have 32 or 64-bit instructions, but the significance, the meaning of each bit, okay, depends on the processor. That's why technically, so for example, what does this one mean, right? Does it mean that I'm going to create, I don't know, like, well, no, usually it's not that. Usually it's um, a is equal to 5 plus 6, okay? Then in assembly, it's going to be add r, add immediate r1 5 6, okay? And in the machine language, it's going to be this, okay? But again, in order to like what, yeah, so for usually the first few bits, that's the code for an immediate instruction, okay? Then some bits, they represent where it's going to be stored into register 1. Then some bits represent what kind of number, that's usually 5, okay? And like the last bit's usually 6. And there are some other bits just which don't represent anything, okay? So specifically what each individual bit means, okay, that's really about how the processor was structured, how it was created, how it was manufactured. Okay, so if I'm a manufacturing processors for TI, if somebody else is manufacturing processors for Qualcomm, of course we have nothing to do in common. I decide that this, I don't know, like this bit should mean, this few bits should mean add immediate. He decides that that should actually come at the end, okay? So that's why people who write compilers, they actually um, have to um, have to modify this part, okay? So the stuff which transforms this, into this, have to be separate, have to be specific for each individual processor, okay? So even like that, unless we're working with Java, of course. Java is machine dependent. But anyway, so modified intermediate code, okay? Then here we come into target code generation. Okay, so that gets us to modified target code. So when we say target, that means specific to processor, which computer program is going to be ran on. And here we come into modified specific. Okay, I'll put it in parentheses. Code improvement. Okay, modified specific code improvement. Sorry, modified machine. Okay. So here, the compiler is going to improve the code, right? But it's going to make those improvements that are specific to each processor separately. Okay. So, for example, it's possible that technically by default, this instruction a is equal to 5 plus 6 is going to be translated into this assembly instruction, which means a is going to be represented in register 1, and then it's going to be stored there later. Then 5 is going to be as a separate number, 6 is going to be a separate number. Maybe it's possible that for some kind of particular computer, a, which is equal to 5 plus 6, will work much better if you do add immediate r1, okay, then r2, and then 6, with r2 having 5 beforehand, okay? So basically we're going to have like two instructions. We're going to load immediate r2 5, okay? So we're going to have two instructions instead of one, these two instructions instead of this one, and maybe again for one particular process it's going to work much better and much quicker. Who knows? That happens, okay? So it is again, it's very specific to, it's very low level, it's very like nitty gritty work, it's very specific to that particular processor, to that particular CPU. Okay, so usually just engineers who have been working for, let's say, TI or Qualcomm for 20 years, they know everything about those processors, and that's usually something they would do. I remember when I was working at TI, we were actually doing something like this. We were just learning specifically how TI processors work, and we try to optimize things, which are try to make them work quicker, okay, on those specific processors. Okay, hope it makes sense. Okay, so the first few phases, okay, up to semantic analysis, serve to figure out the meaning of the source program. Okay, so up to semantic analysis here, right? So basically, I want to have a character stream, I want to have a scan, I want to have a token stream. Like up until here, we're basically trying to understand what did the programmer want the code to do. Okay, so what is the purpose of what we're trying to do here? Okay, so are we trying to add numbers? Are we trying to print them out? So just in general, what's happening here? Okay, and that's why they're called the front end of the compiler. You know, it's like in the web application, you have front end, which is everything you see, and you have a back end, everything which is server related. So in the compiler construction, you also have the front end and the back end. Okay, now the last few phases serve to construct an equivalent target program. Okay, they're called the backend of the compiler. Okay, many compiler phases can be created automatically from a formal description of the source and or target languages. Okay. Okay, formal description, of course, meaning again what we learned in 350 stuff in computer science 350 class. That will be the formal description. So grammatical rules. Okay, so all the syntax rules, grammar rules. Okay, so all of those regular expressions. Okay, so just based on them, compiler can create that I guess like that compiling procedure. Okay. One will sometimes hear compilation described as a series of passes. Okay. A pass is a phrase or set of phases that is serialized with respect to the rest of compilation. Okay, serialized, right? So it's done like one by one. It doesn't start until the previous phases have completed, and it finishes before any subsequent phases start. Okay, so in other words, if we're trying to break down the character stream into tokens, right, that has to be done first. I have to have a complete pass here, right, before I would try to create a parse tree. Okay, I cannot, for example, convert half of the code into tokens and then create a parse tree based on that. I cannot do that. I have to translate the whole thing into tokens, then the whole thing to parse trees, and then, abstract syntax tree, Well, yeah, then this has to be done completely, okay, and then this has to be done. Mm, maybe, yeah, maybe like that. Maybe that can be done at the same time. Okay. Um, Subsequent is a start. Okay. If desired, a pass may be written as a separate program. Okay. Reading its input from a file and writing up its output to also a file. Okay. Okay. So of course, by the way, it really depends on how dig you deep into compilation process. But technically, you can actually stop the compiler again, just based on what we just did, right? You can stop compile at any moment. For example, you can stop it here, okay, and you can take a look at the token stream. You can basically say, hey, compiler, can you please just work until here? Okay, of course, you're not going to get that class file, right? Or just the executable file. And you can stop it there and just like look at the code there, okay? Or you can say like, let me stop here, okay? I remember like when I was coding, again, in grad school, I was doing a lot of C programming, and I learned how to stop the code at any particular moment, and I was able to analyze, like basically I was able to stop here, okay, and I was able to analyze if I did it correctly. I was able to stop here. That's what we're doing actually at TI, okay? We were just like looking at each particular stage, trying to understand if it's possible to improve it. To file, okay? Compilers are commonly divided into passes so that the front end may be shared by compilers for more than one machine, okay, which means target, right? So that the backend may be shared. Hold on. So compilers are commonly divided into passes so that the front end may be shared by compilers for more than one machine. Okay, and so the back end shared by may be shared by compilers, may be shared by compilers for more than one source language. Okay, so in other words, up until some point, okay, you can split that into kind of like, let's say, two halves, right? Maybe like here, here, okay. So once we created a parse tree, okay, like, well, I guess abstract syntax tree, right? After that, we can actually give it to multiple backends, and that compiler can work like, well, I guess multiple backends of compilers, and that can create codes for different target languages, okay, and vice versa. Cool. Okay, that's it for today. On Thursday, we're going to have the first quiz. Okay, it's going to be online. Everything will be open. Okay, it's going to be on the Blackboard. I'll share some details later. Everything which we learned so far is is a fair game to appear in the quiz. Hope you guys enjoyed this class. I'll see you later. Bye bye.